Mhm.
Thank you.
So, around 31 people have joined. Shall we wait for another 1 or 2 minutes?
Yeah, no issues.
Okay, sir, we will start, sir.
Okay, okay.
Okay. So we have Sachin Chaudhary, sir, with us. So he's from Computer Science and Engineering Department, PEC, University of Technology, Chandigarh. So we already had him day before yesterday. Okay, thank you, sir. Thank you for gracing this occasion once again. You can
Okay.
start, sir.
Okay. So, in my last session, we have discussed about the software hardware requirement for the AR VR, and after that, you had some more interesting sessions. Like you had some hands-on also for developing a AR or VR application. Now, I think your last session was on this only, AR VR application development. I hope so. So,
Yes, sir, it was on Spark VR.
yes. So you got some experience how to develop AR applications. So today I'll be discussing about the kind of research that you can do in this area. One part is application oriented. So as we know about like we have UG courses, PG courses, and doctorate also. So in PG course, in UG courses mostly focus on the application development, but in PG and doctorate we do focus on the research direction. So what we can do in case of research for application oriented projects or the task, what we focus upon the existing tools, technologies, and different like programming language or the IDEs which are available, means all the tools and techniques which are available. Okay, but in research direction we try to solve, we try to improve, because all these IDEs and tools or technologies are also developed upon some research. Okay, so what as an academician we can do, we can contribute for some small problems which can solve a bigger purpose in a bigger domain. Okay, one such problem is human action recognition, which is actually my research area, and which is directly helpful in case of AR and VR. We will be talking about some related area as well. I don't know how much time I will be getting today because there is a yoga session also. So how much time I have? First, I would like to tell so that I can frame my lecture accordingly.
So 30 minutes from now, sir.
Only
Oh,
30.
sorry, not. No, no, sir. 90 minutes, 1.5 hour, as
What?
usual.
Okay, okay, okay. Yoga session is not there?
Is there, sir? After your session, we have
Okay.
delayed that session also.
Okay, okay, fine, fine, fine. No issues then. Then it will be good. So,
Oh,
okay. Okay, so I was discussing about the kind of research that we can do. So out of that, I have chosen to talk upon the topic of human action recognition, and I will be talking on the very basic level of work that could be done. Okay, and I will be discussing about the work that I did in the area of human action recognition, the different domain in which you can work upon, specifically in human action recognition. But apart from that, there are multiple area in which you can work in the area of AR and VR. Like there is a topic of depth estimation, foreground background subtraction, or the bad weather, haze removal, or the glance removal. Like there are some distortions due to glass uh, on camera. okay, on in-screen camera. So there are multiple things which are yet to be resolved. So for a effective AR VR system, what we do in case of application development, we depend on the already available tool, but who will provide those tools? And those tools, suppose you are getting a automated character, okay, and you are getting a automatic rainfall, okay, but how perfect that rainfall is, there its shadow is correct or not, its shadow is as per the laws of physics or not, or what if you are executing a AR application in a bad weather situation, will it work in the same way or not? In a hazy weather or in a rainy weather, what will happen? So basically, the in AR VR we depends on the different kind of data from different sensor. It may be a gyroscopic sensor, accelerometer sensor, or any motion related sensor also. But the most important kind of sensor that is to be worked upon is a camera sensor. Okay, the input from the camera, especially in case of AR, not in VR, especially in case of AR and mixed reality MR, the camera sensor is quite important because you are getting two different input. One is the generated reality that you are trying to generate and trying to augment on the real world. Other one is the real scene that you are getting from the camera sensor. So how to tackle this situation, how to tackle the input from the camera, and how to process that input, and what we can do in that direction. There are multiple things that we can do. As I said, you can work in the area of image enhancement, you can work in the area of background foreground subtraction, you can work in the area of object detection, you can work in the area of object tracking, you can work in the area of human action recognition, you can work in the area of gesture recognition, emotion recognition. So many things are there for the scene understanding. Motion estimation itself is a very challenging task, okay, which is quite basic for any scene understanding task. So just I'll share the PPT. Today I will be discussing about the human action recognition specifically. Let me share my screen. Okay, so I hope it's visible now.
Yes, sir.
Okay, fine. So yes. So the our today's talk will be about human action recognition for AR and VR. And again, I would like to iterate, it is one of the case, okay, a specific case study we are doing so that we can go deeper in this direction. Okay, otherwise there are multiple options in the area of computer vision which are directly beneficial for the AR applications, especially. Okay, and these are the kind of tasks that we can do. One part is the application that you might have already seen. You can develop application with the existing tools and technologies. Other one is you can focus upon improving those tools and techniques which are already available. So and the categorization is clear. In case of UG and PG course, your task is to make your student apply the existing knowledge, and in case of PG and doctorate, your task is to help in improving the existing tools and technologies by some concept, by improving some concept or the theories that are already available. Okay, so the same thing we will try to see what actual task we can do. So today's content will be like initially I will start introduction I have given, then I'll be telling the applications of human action recognition in case of AR VR. What are the challenges? Okay, I think human action recognition is important in case of any augmented reality application. This need not to be justified. I hope it is pretty clear. If you will make some kind of simulation, some kind of AR application, some kind of mixed reality application, so human being is one of the most targeted object whose actions are to be identified what he is doing. Okay, so this it is our one of the most prominent tasks that we are supposed to do for any kind of surveillance system or the AR application or a mixed reality application. Okay, their actions are to be known to understand the scene in a better way, and scene understanding is a inherent thing required for any VR application. Okay, so then we will see what are the challenges in case of human action recognition. Then some related literature I included so that you can refer them later. And then what are the databases available, and specifically the databases on which I have worked. Then classification of HAR approaches, what kind of approaches are available. Then I'll be discussing about my contribution in the area of human action recognition, and then what are the future directions of the work. So to start with, what is human action recognition? Uh, it is a very active research area at the moment in the area of computer vision. That is quite understandable because we are installing lots of CCTV cameras around, but even after installing CCTV cameras around, we have to deploy a team to analyze those camera, and they will be sitting in front of the screen all day, and even it's a very boring task to analyze those cameras whole day, because most of the time there is nothing is happening around almost 99% of the time. What we want is, if like some incidents is happening at on a like once in 1,000 time, so that we want to know what is actually happening. Some different kind of action is happening, or some analysis is going on. So that is the automated surveillance, that is called as automated surveillance. Okay, but for that also, what we want to know, we want to know what humans are doing in that scene. Okay, we are not installing CCTV cameras in general for the we are installing for animals as well, but in 90% cases the CCTV cameras are installed for the human being, to monitor the activities of the human being. And why not it should be automatic? On the other hand, if we come to the AR and VR domain, if we are able to if we need to understand a scene, what is going on in the scene, the most prominent thing of course is the activities of the person, what they are doing in that person, so that you can augment a reality in a much better way. Okay, of course there are other things also that you should know before understanding a scene, like the depth of the scene, the foreground in the scene, the background in the scene. Of course they are important to you need to enhance the scene in terms of the quality. So these are also the tasks on which you can work upon. But I have chosen one case, that is the human action recognition, which is also important in case of scene understanding, which is, and scene understanding is must in case of augmented reality. If you understand the scene, then only you can augment a object perfectly. So because suppose you are making an application in which uh, three or five, six people are there, and they are playing with a virtual football. Okay, there is no football present actually, but they are interacting with a augmented reality, AR reality football. Okay, so first you should know that a person in scene is trying to kick the ball. So you have to identify that kicking action. Okay, so you might have some already available algorithm for this in the applications which are available for the development, but they have shortcomings. So we have to focus upon those shortcomings, and we can help them improve by providing some new algorithm for the same task, and even in less computational complexity. Okay, so fine. So what is an action? Basically, technically defining action is a sequence of human body movements, and it may involve several body parts concurrently. This is general definition. From the viewpoint of computer vision, what it is. Uh, the recognition of action is to match the observation with previously defined pattern and then assign it a label. That means we will have some predefined patterns, like the kick ball will be done in the particular manner, the hand waving will be done in a particular manner. There is a pattern of movement or motion. So that existing observation we have to match with a new input. So that is what we have to do in case of human action recognition in a very abstract way. Okay, so depending on the complexity, we have four different kind of actions that are called as gesture, action, interaction, and group activities. Okay, so basic and to gestures are very small level actions, like you are raising your eyebrow or you are just smiling. These are gestures. Okay, then we have actions. Action means you are waving your hand, which includes our limbs, hands, or legs, something. Then interaction, when you are interacting with some other object, like I am saying about the kicking a ball. Okay, then we have group activities. Group activities means you are playing together. You are playing cricket, you are playing football, or you are running in a marathon race or something. In group, you are doing something. So basically, we broadly classify our actions into four different categories. So, what are the major component of a human action recognition system? In general, we have uh, motion segmentation. Initially, the first thing that you have to do is to segment the motion in the scene, and this motion segmentation is not only required for human action recognition, but motion segmentation is a challenging thing for all the computer vision algorithm, and even in case of when we apply a computer vision case of AR, the motion is an important thing to know, and that too in a less computational complexity. At the moment, the methods which are available for motion estimation are very computationally complex. So motion segmentation is the first task that is required to be done. Then feature extraction, of course, and feature extraction earlier we used to do using handcrafted features, but now we are focusing mostly on the deep learning for the correct feature extraction. And then learning and action recognition. So with the invent of deep learning, this feature extraction and learning is part of the deep learning only these days. And finally, classification we can do with any of the classification algorithm. So broadly, there are two parts. One is motion segmentation, other one is the feature extraction classification. Feature extraction classification, which are included in the case of deep learning. Okay, so where we can apply HAR, it can be used for personal assistance. Okay, it can be used for surveillance, patient monitoring, sports, analyzing sports and dance videos, robot human interaction, retail store, shopping mall. And if you'll see all these applications, these are in some or the other way are the future directions of the AR based research, augmented or mixed reality based research. What we expect from AR and VR when we talk about future, what are the future directions, what kind of applications we will develop, what kind of things that could be done. So what we want? We want a virtual assistant. Okay. At this moment, we have NLP based voice assistant, Google Assistant, and Siri. These are pretty much part of our life these days. Okay. In future, you might be having some virtual person standing always by your side. You will be wearing a Google Glass, and always there will be someone to talk like a real person. Okay, but for that you should that virtual person should give actual gestures, actual actions, actual uh, interactions like a normal human being. So but for that you should have strong algorithms for understanding the human actions. Okay, surveillance, patient monitoring again is a task which is in future we used to talk about a lot. In case of like in hospitals, this AR will be very useful. So how we will monitor the patients? So that will be you can find augmented reality nurses in the hospitals which can assist you, like which medicine you have to take, and there will be a feel good factor when there will be someone around you in the hospital always, because having a personal assistant in hospital is a difficult task because there are so many patients to take care. So for uh, like important task, like whenever you are in some emergency, of course there will be a human being, but apart from that there will be some kind of augmented reality person to monitor a patient. Okay, in sports, analyzing sports, robot human interaction, retail store, shopping mall. So they are also some kind of applications which you can do with the human action recognition and AR VR. Okay, what are the challenges? Like you want to make a effective AR application, and which requires some kind of scene understanding in which there prominently there are human beings. And of course, if in a scene there are other things also which are to be done, like as I said, you have to enhance the image. That is another direction to work on. You have to remove any kind of like haze or rain or snowfall is going on. You have to remove those kind of variations in the image. Any camera jitter or any motion, extra motion is there that you have to remove. Okay, of course these are tasks to be done. Then you should differentiate between background and foreground. That is also required to be done. You have to estimate the depth. That is also required to be done. But After that, one of the tasks that is to be done is human action recognition. So that's why we are talking about human action recognition only, but all other tasks are also equally important. Human action recognition, of course, is more important because most of the time our focus is on the activities of the human being. Whenever we are holding a camera or even installing a camera using CCTV camera, our main task is to identify what a person is doing. So what are the major challenges? So first challenge is the anthropometric variations. What are anthropometric variations? uh, can any one of you can tell what is the meaning of anthropometric? So that I should know you are not sleeping. Anyone else? Okay, so no problem. Anthropometric basically means the different kind of body shapes that we have. If you talk about anthropology, it is a study of different kind of human beings in the different kind of races. Okay, so we have different kind of races, we have different kind of body structures, so that size, shape, color is there are too much variations among human beings. We are not similar. You cannot define a one system that fits all. Okay, so certainly we have to generalize at some level, but there are lots of variation. No two people are like 100% similar. There are some differences, there are some odd cases, but in general, I'm saying uh, no two people look alike in all the different ways, like height, color, shape, weight, uh, the body shape, they are different. Okay, so when you will analyze from camera, certainly they are going to differ. Okay, the walking pattern or the running pattern, the way of doing some action is always different. Okay, so first thing is there is difference in the body shapes. So that is a challenge, anthropometric variations. Okay, then we have intra-class and inter-class variations. What is intra-class? Inter-class variation means is in case of like inter-class variation, intra-class variations means same action can be done in 10 different ways. Okay, like if I will wave a hand and you will wave a hand, the pattern may be different in both the cases. So that is called as intra-class. Within the class, there are differences. The action is same, hand waving, but there are lots of variations. The other challenge is inter-class similarities. Okay, uh, inter-class similarities means if you are walking, it's a different action, and if you are running, it's a different action. Though these two are two different class of action, but they look similar. Apart from the speed, there is no much difference. You will walk and run in the same way, almost same way. Okay, so there are interclass similarities. In general, what is the basic rule to define a class or in a classification? There must be sufficient parameters to differentiate between two different classes. And if that is the case, it will be easier for you to classify. If there are prominent features to classify or to segregate one class from the other, then the task is easy. But if the class is different, but still similarities are there, then it is a challenge, of course. Okay, then different weather situations. It is one area which is also opening up at this moment because uh, from like 2 3 years from now or 4 year 5 years from now, we are not focusing at all on different weather situations, but this is a upcoming area these days when we are talking about we have CCTV cameras, but how it will behave in case of hazy weather or cloudy weather or in case of snow, in case of rainfall. So in different weather situations, how your uh, surveillance system or the computer vision algorithm is going to behave in case of different weather situation. Okay, not only in case of human action recognition, but in case of all other applications, like if you want to estimate depth, how you will estimate depth if the scene is hazy or if the rainfall is going on. It is a challenging task. So this is another challenge, which is so in case of other computer vision task, so it is in the case of HAR. It's a challenge. Then variation in viewpoint is another challenging thing, because the action from one angle looks something different and from another angle looks something different. Okay, and it is not the case that you are trying to define action from one angle and person will go through that angle only. He may tilt around, he may walk around in a different way. What you will do in that case? It will be a difficult thing for you to identify if the person walking in some in from left to right, if you will go from other way, then the pattern may look somewhat different. So this variation of in viewpoint is or if you are seeing from the top, the walking will look different, and if you are seeing from the your camera is in the northern side in the same plane, so it will look different pattern, and if the camera is on the top of the head, it will look a different pattern. So how you will differentiate? So that is another challenge. Now another challenge is the privacy preserving. Privacy preserving is coming into picture these days because we are defining so many AR based, VR based applications. We are defining so many kind of visual sensor based system in which we can just give some wave hand to switch on the TV, wave hand to switch off the TV. Like that, some various systems are coming, or even games are there where we can play like real time boxing, in which we will just use our hand to punch the virtual boxing bag. Okay, so there are different kind of games which are available, but what is about privacy? So it is because the all the video that these cameras are recording are getting uploaded to the cloud-based server, where they are getting processed and you are getting the output. So that's why privacy is another challenge that we have to focus upon or think upon. Like in case of recently, Apple launched a home speaker, means voice assistant based speaker like Google Home and Amazon Alexa. They also launched, and what is their most important selling factor is they are saying that we will not record anything that you will say. They are saying this thing, and they are saying that we will preserve your privacy. So it is a selling point. If you develop a kind of technology which are able to develop, which are able to maintain the privacy, then you are you will be better able to solve the kind of application you are developing in case of AR and VR. So these are some of the challenges that you have to focus upon, and a lot of work has to be done in these directions. And if you will focus upon these, you certainly get a good publication in case of HAR. Also, some of the problems are same in case of other domain of the computer vision in case of AR and VR. So I hope till now it's clear what are the challenges. So now talking specifically about HAR, what kind of databases we do have. Uh, these are the databases on which I have worked. After this, there are some more databases. There is a database from NTU University Singapore, which is quite large in size. Microsoft Kinetics dataset is also there, but majorly on which I have worked are JHMDB, HMDB, MP2, UCF101, and UCF Sports dataset. Okay, out of all these dataset, UCF is the largest dataset, having 13,000 videos. If you will talk about NTU, it is I think having 40,000 videos, and its size is about 165 GB. So you need to work on a lots of data. So that you should always think when you are talking about some kind of research in the area of AR, VR, or scene understanding, computer vision, or any sensor-based research. Especially in case of computer vision, you are required to deal with lots and lots of data. So this is UCF 101 is having 13,000 videos, so you can imagine what kind of size it has. So you need to have very good computational complexity, for which you can develop labs in your organizations or institutes to process this kind of data. Okay. So, based on the literature, I have summarized the kind of approaches which are available. Okay, you can opt for the any kind of approach that you wish to work with, and of course, there will be a new addition if you will work and you will be able to provide a good result by using that approach. But what is the state of the art approach that is being used these days is a CNN. So basically, we have two different kind of approaches: handcrafted approach and learning-based approach. Like 5 to 6 years from now, we are totally focusing on the handcrafted approach, where we have spatio-temporal based, depth based, trajectory based, and global approaches. In learning based approaches, initially we tried genetic algorithm based approaches, dictionary learning, neural network based approaches, hybrid model. Then in neural network based approaches also we have learning static frames, learning frame transformation, learning handcrafted features, and then finally CNN. And CNN at this moment, convolution neural network, I hope you might have heard about convolution neural network, because it's a kind of buzzword these days. So it is a very effective mechanism in case of any classification task, in case of images and videos. So this is the broad classification of the kind of approaches available for human action recognition. So in any of the model that you will be using, any of the tool or ID that you will be using, and you will be trying to use some human action recognition task, then or any classification task in your AR and VR game development, that classification might be somewhere using CNN at the back end. Okay, so or maybe some different form of deep learning, different kind of architectural model for the deep learning. So this is the classification approach. You can go through some of the approaches if you want, or you can just check it. It will give you a kind of view that what kind of work could be done or what kind of approaches could be there for solving a particular task in case of human action recognition. Okay, so now, as I said, the first task in case of any computer vision based algorithm for AR, VR, or scene understanding is the estimation of motion. It is a very challenging task. You cannot define a system, or you cannot make any application without estimating the correct motion. Right now we are talking about the motion estimation case of human action recognition, but even in case of autonomous driving also, you want to estimate the motion of car, you want to estimate the motion of the people walking around the street. In case of simulation also, in some kind of experimentation you are doing using AR, VR, some kind of game you are developing, you need to identify the motion. Then only you can define effective reality, effective virtual reality, or effective augmented reality, if you will be able to identify the motion. So what are the two major algorithms which are available for optical flow? Although there are hundreds of algorithms available at this moment for motion estimation, but most of them are based upon these two. And out of these two also, these optical flow and motion history image are the two most effective method or well-known method for the motion estimation. And on the top of that, mostly on the top of optical flow, you will find hundreds of latest method available which are computationally more efficient. But instead of going into the discussion of different kind of optical flow based methods, I thought of discussing about the actual optical flow which was initially proposed. So these are two different methods for motion estimation. You can use either of them, either optical flow or motion history image. The difference, major difference between these two is optical flow is computationally very expensive, because if you will see, if you want to go through the derivation of optical flow, you will see it requires lots of mathematical calculation. Then we have MHI, motion history image, which is quite simple to calculate. It is like the simple subtraction of the frames having some threshold value. So we will see that in detail. I have one contribution in the side of MHI. So MHI is straightforward, simple, but the output is not as effective as in case of optical flow. Because effective, when I'm saying, that means it provides direction and velocity information on each pixel. That means in which direction the pixel is moving. Uh, MHI do not provide in direction and velocity information, but optical flow provide motion among two consecutive frame, or MHI provides whole span. So apart from this, we have dynamic image network. But before going into the detail of this, I would like to ask you what is motion? What we can call as a motion in case of videos? How in very basic language, in very abstract way, if you any one of you can tell what is motion. If I'll ask you to, you just tell me if there is any motion or not in this video, what how you will identify. Anyone? Yes. Yes. Anyone else? Okay, no problem. Uh, so you rightly said it's a change in coordinates, you can say, but in general, coordinates do not change. The intensity on the coordinates do change. Okay, coordinates will remain same. So the most basic way to identify motion is there are two frames, frame 1 and frame 2. Okay, in pixel 1 of frame 1, the intensity value is 10. Okay, now next frame is frame 2. We will check the pixel intensity on the pixel 1 of frame 2. If it is 10, that means the region is same. The pixel is same in both the frames. Okay, if this intensity will change, now if we will have 11 or 12, so that means there is some motion, there is some change in two different frames. But this is not this simple, because whenever you will click a picture, this intensity is bound to change even in a static scene as well. You click one image now and you click one image 1 second later, and you check the pixel 1 of image 1 and pixel 1 of image 2. The scene is same, lightning is same, still there will be some minute differences in the intensity. It depends on the kind of light that you are having, because light, even our best of the lights are not constant. Okay, there are some flickers in the light, even in LED, CFL, any kind of light you will use, there are some flickers. So the light in the intensity is not always constant, it will differ. Okay, so in this definition is pretty much okay, that we are saying you just differentiate and find out the difference. This is a motion. Okay, but is it prominent enough to be considered or not? That was a challenge. Okay, that's why we have gone for a computationally expensive method, that is optical flow, which will provide us the motion, like in next frame, in which direction it is going. This pixel is moving in which direction. Okay, this also it will provide. So these are two methods of to calculate that motion. We have two methods, and I will tell how I contributed, how I got a publication in that direction by contributing in that motion estimation. That will be in next slide. Before of that, let us discuss about dynamic image network. So dynamic image network is another way to summarize motion. Okay, in dynamic image network, it was a paper published in CVPR 2017 or 16, I think. What they did was they tried to summarize the motion of the whole frame of the whole video into one frame. Okay, and they were able to get good result in case of human action recognition, and they just overloaded pixel 1 of frame 1 with the average of all the pixels in the video of pixel 1. So just they try to overload that information using some ranking function. So it was another way to summarize motion. They were also able to find out motion in some innovative way. Okay, so what I did and how what publication I got, I'm discussing that in my some of the contribution I will discuss, which are related to human action recognition. So this is my first contribution in case of human action recognition using Weber motion. So as I said, uh, the change in pixel intensity over temporal direction is called as motion. Okay, This is the definition of motion. Change in pixel intensity over temporal direction is called motion. But as I said, there will always be a change most of the time. So simply this definition do not work as it is. Theoretically, it is very much correct. Practically speaking, if you will just go for the change, any change if you will consider as motion, you are going to get a lot of noise. I'll tell you how. Because this even if you will make this lightning constant and other factors, you make all everything constant, your camera quality is also very good, your exposure, your shutter speed is also constant, camera shutter speed, so you will absorb same amount of light. So I'm saying about the lab conditions where you are keeping everything constant. Okay, but you cannot keep the background constant. If you will work in a real-time scenario, the background leaves might be moving, the background some scenarios, if your wind is waving, some kind of objects might be moving at the back end. If suppose it's a dense scene and there are lots of trees behind, then of course the leaves will move. Okay, so there will be lots of unwanted noise that you do not want. Okay, these are that noise, that motion, that as per definition it is a motion, but you do not want that. So what I thought was, let us define motion in more appropriate way. And for that, there is a definition of motion in physics. Okay, which is called as Weber's law. Okay, you can also go through this law. Weber's law specifically defines the motion, what you can consider it as a motion. So it should be some kind of ratio. Every change cannot be considered as a motion. There has to be a constant ratio of delta I to I, means change in intensity to actual intensity. It has to be above certain threshold, then you can consider it as a change. Okay, and why I thought of this is because the optical flow was computationally very expensive. Okay, and in case of human action recognition, we can work with motion history image. But the problem was, as I said, we are getting lots and lots of noise. I will show you the output of our motion history image without this Weber's law. Okay, so uh, using Weber's law, we can segregate this unwanted noise. And as I said, motion history image is computationally very efficient, so we can uh, utilize it for the human action recognition, so that our computational complexity will also be very low. That's why instead of focusing on optical flow, I focused on motion history image because it was computationally efficient. But the problem was noise, and I tried to remove that noise and tried to get the output from that. Okay, so in MHI there are majorly two problems. One is parallel action. If one person is standing behind other person, so that time it is difficult to identify motion history image. Okay, motion history image is basically subtraction of consecutive frames. Okay, so that you can get the history of motion, like where the pixels have changed over the temporal direction. Another one is erroneous motion. So erroneous motion means the background motion or the very minimal motion that you will get, which should not be considered, but it is uh, wrongfully considered as motion. So with this approach, we are able to tackle the problem of erroneous motion. This was the the overall pipeline of the proposed approach, in which we have taken an input video and we tried for pose extraction. This pose extraction was done using the joint positions in the database, but it was published in like 2017 or 18. So now we have in 2019 we have very good paper for pose estimation. So this was annotated pose estimation, but now if you will try, you can go for automated pose estimation as well, in which you will get the pose estimation from the network itself. Now then we have divided the image into different block according to the joint positions in 5 different block, like left image, full image, left image, right image, upper, lower, like this. In 4 parts we have divided, and we've tried to find out the motion of each patch. Okay, and then we have extracted the motion, uh, uh, features using VGG16 from the frames, and this motion features we have extracted using FlowNet. And then we have done aggregation of both the feature motion and image features, which is a very common pipeline in case of human action recognition. You extract the RGB features for the features from the RGB appearance based features, and then motion based feature you identify, and you merge both, because to identify action you require both. You require motion as well as appearance. So the rest of the part is very common: appearance based feature and motion based feature aggregation, and then concatenation. Then finally we have gone for the classification. Okay, so the architecture of VG16 and VGG FlowNet is also given here, the kind of configuration I have used. So this is one contribution, and for this is the flow chart, the process that we have followed. We have taken input image, we applied LOG, then Weber's law, then some morphological filtering we did. Now important thing is to see the figure 4. In figure 4, if you will see the B is the actual MHI. You can get code for calculating motion history image on the net also, and you can try it using by some putting some threshold, or you can try it as it is. It is very simple code. You can get it. You can get code for optical flow also. So you can take a video and try to find out its motion history or its optical flow. So here, see the motion history image, actual motion history image. So much noise is there. And if you'll see the image C of figure 4, it's a optical flow, and you see how crispier output we got. We got exactly what we want. We want, see, rest of the part is static, only person is moving, and we want that. So we got our region of interest in case of optical flow. But now see D is a filtered output from B. Okay, where when we applied Weber's law on the motion history image, we got this kind of output. And you can see the claim was like it is not better than optical flow, because optical flow provide direction and velocity information as well, but the computational complexity required for WMHI is far less as compared to optical flow. So we can compromise up to certain level on the output when our computational complexity is very low as compared to optical flow. Okay, so output is also almost equivalent to optical flow, but computational complexity is far less. Okay, so these are some results that were the output of that work. So as you can see, we got a very good result in all the different databases that we have used, and which are almost uh, for 6 to 10% better, 7 to 10% better in all the different databases, JHMDB, MP2, and some JHMDB. Okay, so in case of time also, we are taking far less time as compared to the optical flow based method. So all these results are given. You can analyze these results. I will share the PPT. You can see these results, or even paper is also available online. You can see the title of the paper and can read it. If you want copy, I can share. Okay, so this was one contribution, just to give you some intuition that what kind of work you can also do. Then we have depth-based method. So as I can personally tell you, the depth estimation is one of the most important tasks. Okay, for any kind of AR-based application. And intuition about that I have given you in my first lecture also, that Apple has included the LiDAR camera now. Okay, so why they have included LiDAR camera? They clearly claimed for a better AR experience, they have included the LiDAR sensor in their phone. LiDAR is a costly camera. If you will see, the camera cost is like for I think it's around 20-30,000 rupees. I think only camera, LiDAR camera, and it is used for depth sensing only, or laser-based depth sensing. Okay, so what we tried to did was we tried to extract depth without using LiDAR camera. Of course, the output from the LiDAR will be better, but we tried to extract depth, and from depth we tried to extract human action recognition, and we got success. Our result was good as compared to the existing method. So my second contribution was on depth-based method, depth-based end-to-end deep network for human action recognition. Okay, so basically this single image depth estimation is a very common task which is done in case of haze removal, or image enhancement kind of task. So what I thought was, the color information is not required. For motion estimation, you don't need color information. Then why to process color information? For processing color information, we require to process three different channels. Okay, RGB channels. So this was my basic idea. Okay, why not let us try to estimate depth using the concept used in mostly used in haze removal or image enhancement task. Let us try to estimate depth, because the depth camera used to provide better results if we have depth information, but we try to implement that in the videos where depth information is not available. Okay, we chosen the data set where we do not have depth videos available. Like for NTU data set, we have depth videos available with us. Okay, so I have not chosen that database. I have chosen the database where depth information is not available. So this is what we did. Our approach was divided into four parts. So first we are estimating depth from the normal RGB videos. It is not an input from LiDAR or Kinect sensor. It is a normal RGB video. From depth we are estimating motion. Then we are going for feature extraction and classification, which is common task at a later stage. Once you have the right kind of input, then you have to go for feature extraction and action classification. So here, first we did depth estimation. For depth estimation, we have utilized a network which is called as multi-channel, multi-scale CNN. We applied CNN in different channels. Okay, so and from that we got a depth estimation, which is a byproduct of that particular network. Okay, this is a multi. If you will see here, the input video frame will go for color fusion initially, and then it will go for multi-channel, multi-scale CNN. Okay, if you want to see the details of this network, you can go to the paper. It is also available online. And from that, we are going for depth estimation. So this depth information we have utilized for extracting appearance-based feature, and depth gradient estimation we did for the motion estimation. And again, we have utilized VG16 for the feature extraction from the depth images, and FlowNet for the motion images. And again, after that, we did the concatenation of the feature, and then finally, we have gone for the classification. So this is our second approach. This is the architecture of the multi-scale, multi-channel network. The initial input image will be divided into three different channels RGB, and then the CNN will be applied on three different channels, and then pooling will be done. So this is a kind of architecture that is being proposed for the depth estimation. And after this depth estimation will be given as an input to the for appearance-based feature extraction. These are the output of the estimated depth, where we have sample image and estimated depth. You can see the object which is nearer to us is having more intensity, and objects which are away are having lesser intensity or are looking like black. Okay, objects which are closer. So basically you can segregate the foreground and background with this. And in our case, mostly what we expect in foreground is a human being or some action is being done in the foreground, and background we want to segregate. Okay, so this for temporal gradient, we did feature extraction as I explained already. So this was the experimental results. You can analyze these results from the paper. This is the comparison. We almost got like very good result on UCF. It was 94%. We got 97. In case of HMDB, it performed exceptionally well, and we got very good result on HMDB, 51. Okay, so now this is a comparison that why we have used our two-stream network. So if we'll use appearance-based feature, the output is less. If we'll use only motion-based feature, the appearance is less, the accuracy is less. But if we combine those features, the performance improves. Okay, so this is also available online. Then we have another contribution, that is in the area of all-weather intelligent surveillance system. As I said, the weather is a challenging issue. Different kind of weather situations are a challenging issue. So uh, what we should do in that case. So I particularly focused on the haze, because haze is one of the challenge. You can go for the rain also, you can go for the snowfall also. So it is up to you. I focused on the hazy situation because in northern India it is a very difficult situation in winters when there will be lot of haze, and you might have also seen the air flights will be delayed, the air trains will be delayed. So I focused on the haze, what our surveillance system will do in the hazy scenario, or even if you develop a AR VR application, how it will behave in the hazy weather. Will it be able to behave in the same way or not? So this was our contribution, motion estimation in hazy videos, where we initially tried to uh, remove the haze. This is the network architecture for haze removal, where we have used the input inception module from the Google Net and encoding module. This is the architecture. This paper is not available online as of now. Okay, so but this architecture is it is available. You can find these inception module details of inception module. So I have not included the exact details of the architecture, but over basic idea you can get from this. Okay, so here what we tried to did, we tried to estimate optical flow from the hazy video. So it was distorted, but when uh, uh, when we remove the haze from the non-hazy video, the optical flow was somewhat better. Okay, so the network details of that particular paper I'm not just discussing at this moment because that is under review. But some basic idea you can get from the architecture that I have shown. Okay, uh, okay, fine. Then we have action recognition in hazy video. This paper is available online. So here, see what we did. This is the hazy input video. First thing that we did is we tried to create hazy videos. Okay, uh, we tried to include haze in the existing data set, and then we have used dehazing using this network, using the concept of air light estimation and multi-channel, multi-scale CNN that we have utilized in our other paper also. We tried to remove the haze, and after that we utilize the concept of dynamic image network, a concept given in dynamic image network paper, that was for rank pooling. So that rank pooling concept we have utilized here to find out a summary of motion. So you can see that we have tried to find out motion in some intuitive way rather than going for, because this network is already preloaded with the kind of de dehazing network where we are trying to dehaze, and if we'll further go for the analysis of the video again, uh, for a whole video, it will be a very computationally complex task. So what we did, we applied the concept of dynamic image network to find out the summary of motion, and then again we have followed the same pipeline, which is very common in case of human action recognition, like for appearance and motion based features. Okay, so this was in the direction of different hazy weather situations. So we conducted one experiment to justify that hazy weather is a problem, because this was the first paper in the direction of hazy weather, in the direction of uh, hazy weather in case of human action recognition. So we have to establish that this is a problem. Okay, so what we did was we applied existing method on the hazy videos, and what we saw in this table, you can see the third column where it is written like DE, which is decrement. There is a decrement of 7 to 8, like 4 to 7%, or 4 to 5, 4 to 6, 7% in all the existing methods when we applied haze in the existing data set. So it was a problem if their performance is decreasing, and then we have applied our method, and we have seen that our method is giving the best result as compared to the existing ones in the hazy weather. So this was the task. Three different experiments was done. Another one is HAR in low resolution video. I utilize this concept for the privacy preserving, because if you will, there are two major benefits for this. One is if you can find out actions from the low resolution videos, then there are two major benefits. One is the size of data to be processed will be decreased. Then privacy preserving of the end user will not be compromised. I'll tell you how. So if you can see in this image, you can see in figure 19, this is a low resolution image. And okay, visual results you can see. So you can see that image second image, you can see the person is visible in the actual image. What we did, we reduced it to a very low size, that is 12 by 16. And when we tried to uh, upgrade it using bicubic interpolation, you can see the hands are visible, but the face is not visible. Okay, so this can be one of the idea to preserve privacy, as well as if you are decreasing the size and you are getting the result in a low resolution video, it will be of great benefit in terms of the size of data to be processed. Okay, so this was an approach of human action recognition in low resolution videos, and you can see the output. Uh, the output in the E column is the output of our proposed network, which is slightly crispier than the output of the bicubic interpolation that is shown in C. And once we are applying the optical flow method on these images, you can see the difference between D and F. F is the output of our method of calculating optical flow from the enhanced image using the concept of super resolution. Okay, so you can see the optical flow after applying our method is more crispier as compared to the optical flow from the bicubic interpolation method. This is the overall network for the proposed work. So you can go through this. Okay, this is the some results that we have got. Then another method is the post-based method for human action recognition, where we are trying to estimate pose. So this method is particularly beneficial in the kind of application where our target is human being, like you are playing, you are making a AR-based game. Our target is person, what person is doing. Okay, we are not focusing on the surrounding scene, understanding or something. So we have this is a pose-based method. So it will first try to identify the pose of the person. Okay, so I'll tell you how it is. This paper is also available online, so you can go through this. So this is our input frame. We will try to estimate pose. So this kind of pose you will get based on the joint positions. And then we did region pooling to find out the actual, to discard the background totally. Okay, so now we have only a specific region available for the person. Okay, and all the background which is required to be processed unnecessarily is being done away. So our processing will be a bit faster. So this is the network architecture. Initially we used VGG19 and a part affinity field module for the finding the part affinity. Like you will find initially the joint position, and then you have to find out which joint is to be connected with which joint. Okay, so the part affinity has to be find out. Then we will find, we have a confidence map module. Someone is trying to say something. Okay, so then the output of these two modules will be pose estimation, estimated pose. So in this pose estimation, we will do region pooling, and we will try to find out the actual area which is of our concern. Okay, and then we will do the human action recognition, and you can see the output here. The B is the dynamic image. So here we have utilized the concept of dynamic image that we have in our motion estimation slide. So here you can see the dynamic image from the normal frame is having some background noise. Okay, and the dynamic image using our method is not having that kind of background noise. Here only the actual region that is to be identified is provided. Okay, so this is a quantitative result that we have got, and this method has certain limitations, like it will be good in case of only person-centric videos, where background scenario is not that much, only focus is on person. So now to the future research, what you can do. So the all the work that I have discussed, it opens up the research area for HAR in different weather situations like haze, snow, and rain. The work can be extended in the direction of low resolution action recognition to reduce computational complexity. The work can also be extended to propose different dimension of privacy preserving in HAR. So uh, that is all in terms of human action recognition. Apart from this, so these are references. You can go through these references. I have kept for your reference so that you can just refer to them at a later stage. So this was what uh, was to be discussed in case of human action recognition. Apart from this, if you have any question in this, you can ask now. And whatever we have discussed, if you have any questions, you can just ask. Okay, I'll take more questions one by one, which are here. Are these datasets are freely available? Yes, they are freely available. They are publicly available. Even NTU is also freely available. They are provided by universities, and uh, just in some cases you need to mail them to take the credentials for downloading. And most of these datasets which I have discussed are freely available. Okay, so no need to pay anything for these datasets. Why CNN perform better than evolutionary computing? Is there any formal proof that justifies this? Yes, they because see, if you understand CNN, so basically what we are doing in CNN, we are trying to do the most basic operation, that is convolution operation. Convolution is what? Convolution in case of image processing, what convolution we are applying, it is actually the concept of convolution you can learn from signal processing. But what simply we are doing, we are just multiplying. It is kind of filtering, dot product we are doing between filter and the image. So it is the simplest operation, okay, with which you can find out the features, okay. And those features, if you will combine this feature extraction, if you will combine with the learning process, okay, like back propagation, and you will try it, you will complement it with a suitable loss function and weight updation method. So over the duration of time, it is 100% sure that you are going to get a nice complex feature for that particular problem. Okay, so that is why CNN is a very simple operation to do for the filtration. It is computationally easy. Also, when combined with a good back propagation algorithm, it will help us learn more complex features, which we cannot actually uh, do with the in case of our handcrafted features. So the complexity of data in case of images and video is that much that we cannot uh, we cannot simply uh, define all the features required for the problem. That is why it in general it performs better than the other approaches we have. It is a base for all the networks actually. So I think if you go through the approach, you automatically will understand that why it is better at this moment. Maybe in future we will get something else, but at this moment it is the simplest thing that you can do to extract features. Okay. Any other question or any other counter question to this? So any question? No questions? Okay. Okay. How to determine number of hidden layer required for a particular problem solving? See, there is no fixed formula for that. It is most of the time it is a hit and try method. Although you can talk about the loss function different similarity measurement or error correction or the weight updation algorithm, initialization algorithm for a specific kind of problem or the kind of pooling function you have to use. But number of layers generally depends on the kind of problem, and it is determined by the kind of problem that you have, which is generally done by hit and try. Okay, there is no fixed formula. I can tell you for classification you should have this much, for regression you should have this much. There is no fixed formula for that. You can try, you can one thing I can tell you, you can visualize. Okay, now we have very good uh, uh, tools available for visualizing the output of the network. You can simply plot the output after each and every layer. Okay, what's the output that you are getting, and you can fix your target that this is this kind of feature I want. This is something that I should get. Okay, and using that visualization, you can just change your network. Like initially you tried with this many number of hidden layer or this many number of layers or this layer after this layer. So any architecture you have developed, you just visualize your outputs in one or two iterations or maybe after every 10th iteration, what kind of features you are getting. Are these the actual features that you are supposed to get, or what you have planned for in that network? If these are coming to be correct, then you can go with that architecture. Otherwise, you have to update your architecture, but you will get an insight. So that visualization of the network is one of the solution with which you can get the answer of your problem. But there is no fixed formula that you should have 4 layers or 3 layers or 5 layers for this particular problem or the data in case of images. Okay. Yes. Any other question? Okay. If no other question, just I want to conclude with some discussion. That is, we have discussed about the human action recognition. Okay, which is one one of the problem in case of AR and VR. Okay, the computer vision is an inherent part of any AR and VR technology. Okay, so initially I talked about the application and research part in case of AR and VR. For application part, you had session earlier. I totally focused on the kind of research that you can do, and I tried to uh, make it intuitive for you so that you can think what kind of work could be done. So research work are generally done at a very small scale and in a very core level and on a specific problem. You will be solving a very small problem, but it will be helping to solve a bigger purpose for others. Okay, that is what in academic research we do. So similarly, in case of AR, VR also in AR, VR, as I said, there is use of all different kind of sensors. Okay, but when we come to AR and MR, the use of camera sensor is too much. Okay, and we need to have input from various different sensors, but the most prominent input that we will get is from the camera sensor, and our task is to process that, and that domain is called as computer vision. In computer vision, we have lots of uh, problems, lots of challenging problems that are to be discussed, and I talked about background subtraction, foreground extraction, or haze removal, bad weather situations, or image enhancement, or glance removal, or human action recognition, activity recognition, or scene understanding. All these things will comprise or will be part of your AR/VR application. Now it is up to you to utilize the already existing algorithm or to propose new one for the same task which are better than the existing one. Okay, so out of all these problems, I have discussed about human action recognition, in which I have discussed about my contribution in that direction, plus the major challenges on which you can work upon. So I hope you might have got some motivation from this lecture to work in the area of computer vision for AR and VR. If you want to work in case of human action recognition, you can contact me. You can read the papers which are available online, or if you want any help from my end, I will be available. So no issues. So that's all from my end. Still, if you have some question, you can ask. Otherwise, I will leave.
Participants, do you have any question?
I think no questions.
No questions.
So thank you then from my end.
Thank you, sir. Thanks a lot for such an interesting and informative sessions. So both the days, and thank you for your clear, excellent, and clinically oriented presentations. Thanks a lot, sir. It's a privilege to have you here. Thank
Okay, sir. Thank you.
you. So, any of the participants, if you have any research doubts or ideas with respect to whatever sir spoke, you can contact him. If any other doubts you're having, questions you're having, you can ask. Thank you, sir. It was extremely helpful for all of us. Thank you, sir. Yes, there is one more session. Okay. So there's one more session on stress management. I'll let you know the timings. Just a minute.